5 more Angular Kinematics problems here. This one has a situation in which the acceleration is not constant. And you can tell this because in the polynomial that we have here, the angular displacement goes up through the 4th power. So deriving an expression for the angular speed, derive means start from first principles. So the relationship between theta and omega is you take the derivative of theta and that gets you omega. So if we take the derivative of that expression given at the top, the 4 comes down, multiplies by the existing coefficient, and then the exponent reduces by 1. And the same thing will happen with the b term as well as the term with the a in it. And then we can do the same thing for the angular acceleration. Deriving means start with the relationship between these variables. In this case, we're going to take the derivative of the angular speed. So we will start with our answer to the previous section. Taking the derivative means the exponent comes down, multiplies by the existing coefficient, reduce the exponent. And that holds true down the line. Now in this case, for a, this is the same thing as saying a t to the 0. So when the 0 comes down, 0 times anything is 0, and that term disappears. All right, for part C, in terms of the givens, so we will expect to have A's, B's, and C's in our answer. We will find the times at which the speed is at a maximum or a minimum, and then what those speeds are. So we're going to have 2 assignments here. First, we need to find times, and then we need to find speeds. So finding the times when the speed is at a max or a min, that's when the acceleration is equal to 0. This is known as the first derivative test in calculus. So we're going to set the acceleration equal to 0 and take this expression and solve for the times. So 12, that's a C. Squared plus 6bt. And we can factor things out and divide because we have a 0 on this side. So we'll have 0, factor out a 6t, and then we will have a negative 2ct plus b left inside the parentheses here. And we can set each factor equal to 0. So 6t is equal to 0, divide both sides by 6, and then t is equal to 0. And then negative 2ct plus b is equal to 0. Solving for t gets us b over 2c. So the speed is, or the acceleration is equal to 0 at these 2 times. And when the acceleration is equal to 0, that tells us that the speed is either a maximum or a minimum. So we can take the 2 times and insert them into our above expression. So if we plug in 0 for t into this top expression, we get the original speed of a. If we plug in b over 2c into this expression, we get a plus 3b, b squared over 4c squared, minus 4c, then b cubed over 8c cubed. Now these 2 terms can be combined, but we will still have a plus a here. So our combined and simplified terms end up being a plus b cubed over 4c squared. And that's the 2 speeds that are either maximum or minimum. All right, problem 2. We have a constant angular acceleration. This is just a number. And during some 4-second time, it's going to turn through 120 radians. We're not told what the original speed is or what the final speed is, but we can calculate the speed at the beginning and then at the end of that 4-second interval. So using our organizational system here, it's accelerating at 3 radians per second squared. And it's during 4 seconds that it turns through 120 radians. And we're looking for the original and the final speeds. Now we can get the original speed by using this kinematic equation, because we know theta, we know t, and we know alpha. So 120 is equal to omega times 4 plus 1/2 3 4 squared. Arithmetic, and then subtract it, and then divide by 4. Doing some arithmetic and algebra gets us an original speed of 24 radians per second. To get the final speed, omega f equals omega naught plus alpha t, we can use our original speed of 24, the angular acceleration of 3, and then those 4 seconds gets us 36 radians per second. Now, what if the wheel started at rest and then it sped up to the beginning of that 4 seconds? So let's back up our list here, and it will have accelerated at 3 radians per second squared. And we're telling you that it started at rest. And then at the beginning of those 4 seconds, that's when it reached 24 radians per second. So the beginning of this 4-second interval is the end of whatever this time is that we're looking for. So omega f equals omega naught plus alpha t. And this time we know it's going to end up at 24 and it started at 0, but what we don't know is how long it took to get there. So in this case we can subtract the 0, divide by 3, and we get a time of 8 seconds. It was spinning for 8 seconds before it got to that particular 4-second interval. We have a merry-go-round here, and it's going to accelerate with constant speed, so we can use kinematics again. Constant acceleration. So 1.50 radians per second squared. And it starts at rest. And we're going to look for the amount of time that it turns through those first 3 revolutions. Now, because we have radians and revolutions, we will need to convert from revolutions to 2 pi radians, which gets us 18.85 radians. And we're looking for the amount of time. So theta equals omega naught t plus 1/2 alpha t squared. That turns out to be 0. 18.85, 1/2 of 1.5, don't forget to take the square root, 2 theta over alpha. This gets us a time of 5.01 seconds. Now we're going to let this thing continue to spin, but we're going to restart our stopwatch, and the question is, well, how long does it take to turn through the second 3 revolutions? There are a couple of ways that we could do this. One way would be to start from the beginning, find the total time for the first 3 and the second 3, which is 6 revolutions, or 2 times the 1885, which gets us 37.7 radians. When we get that time, we can subtract these 2 times, and that's the amount of time that it took for the second set of 3 revolutions. So we can go through the same calculation, but with a slightly different angle here. So 2 theta, the second one, and this gets us a time of 7.09 seconds. But now that's for all 6 revolutions. So T2 is the 7.09 minus the 5.01. It's that change in time. So it's 2.08 seconds. Now this ratio is going to be changing because we're going to be adding the same theta for each set there, but then we're going to be taking the square root. So finding the ratio between each set of adjacent 3 revolutions times is going to produce a ratio that tends towards 1. It's going to start out at about 2.4, maybe 2.5-ish, pretty close there. But then as time goes on, that ratio is going to get closer and closer. The last 2 problems will go on the next video, as I'm running out of time available on this video. All right, problems 4 and 5 of more Angular Kinematics problems. We have a wheel with a radius of 0.5 meter, and it has a constant angular acceleration. This negative indicates it's going to be slowing down, and it turns through 120 radians. This is a similar problem to a previous one in which a wheel turns for 120 radians, except this time it is slowing down. So, as long as the angular acceleration is constant, we can use our kinematic equations, and having a kinematic list will help us with that. So it's slowing down at 3 radians per second, and for a certain 4-second interval, it will turn through 120 radians. Question is, how fast was it going at the beginning of that time? So we can use our no VF equation, in this case no omega F, to calculate how fast it was turning at the beginning of that time. So we have 120 radians, 4 seconds, negative 3 radians per second, and then 4 seconds squared. So adding that to the other side and then dividing by 4 seconds, we get an original speed of 36 radians per second. Now, how much time will it take to stop? Now we're going to switch around a few things here. Now that we know that it was traveling at 36 radians per second, it's going to stop. How much time is that going to take? And it's still decelerating at 3 radians per second squared. We don't care about what angle it turns through just yet. So, picking your favorite kinematic equation that has a time in it. In this case, we have 0, 36, minus 3 nt. Solving for time gets us 12 seconds. The linear speed of a point on the rim is related to how far away from the axle it is, as well as how fast is it spinning. And in this case, let's calculate the initial speed, so that will be omega, corresponding to omega naught. So the radius is 0.5 meter, because the diameter is 1 meter, and the original speed is 36, so the original linear speed of a point on that rim is 18 meters per second. Now the total angle, if we come back to part B, now we're going to look for the total angle. So theta is going to be omega naught times the time that we have there, plus 1/2 alpha times squared. And we know how long it's going to be rotating, so 36, 12, minus 1/2 of 3, and then 12 squared, gets us an angle of 216 radians. We could also have used the no t equation to calculate that same thing, knowing that as it stops, that tells us that the final speed is going to be 0. And the original speed was that 36 that we calculated earlier. Don't forget to square it. And 2 times our angular acceleration is going to be 6. So 36 squared divided by 6, that also gets us 216 radians. All right, the last problem in this set, we have the Earth spinning, and we're near Philadelphia, just outside Philadelphia. So here's the center of the Earth, and the equator there. If you're spinning, it doesn't matter where on the Earth you are, you're going to be spinning with the same angular speed, but your linear speed is going to be a little bit different. So we need to get rid of the line there. Philadelphia is at about the 40th latitude. So the circle that Philadelphia sweeps out is smaller than the circle that the equator sweeps out as it spins around. So if we look at the radius of the equator, radius at Philadelphia, there's 40 degrees there. But the linear circle that gets traced out is smaller. It's going to be the cosine piece of that triangle there. So radius of Philadelphia is going to be the radius of the Earth times cosine of 40 degrees. So that will be 6.37 times 10 to the 6th times cosine of 40. And that gets us 4.88 times 10 to the 6th meters. Now, the Earth spins once every 24 hours, so omega is going to be 2 pi divided by 24 hours times 3,600 seconds in an hour. And that gets us 7.27 times 10 to the minus 5th radians per second. So the linear speed of Philadelphia as it spins around is going to be the angular speed of the Earth times the radius of Philadelphia. Notice it's not radius from the center, it's the radius of the circle that it sweeps out. So that's 4.88 times 10 to the 6th. So we have 7.27 times 10 to the negative 5th times 48.8 times 10 to the 5th. We move the decimal point, change that guy, and this way we can cancel those guys and just multiply 7.27 and 48.8, which gets us about 350 meters per second. Now, if we're on the equator, we don't need this cosine of 40. What we have is the 6.37. So the linear speed at the equator is the same angular speed as Philadelphia has, but times the radius of the Earth. And that gets us, using those two numbers, 463 meters per second.